In this lecture, I'm going to be bringing together everything that we've covered in the last several lectures, and we'll see how this can be used to find black holes, which has sort of been our goal all along. The way we're going to do this is using something called X-ray binary stars. Binary stars, of course, are ones where there's two stars that are orbiting each other. And in this particular case, we've got either a neutron star or a black hole that's being orbited by a main sequence star or a red giant or something like that. And just like we had with the white dwarfs, since neutron stars and black holes have very high amounts of gravity, they can suck mass from their companions. And this gas then heats up and gives off X-rays, which we can make measurements on. And it's by studying those X-rays and doing spectra and all the kinds of stuff we've been talking about that we can find black holes. You may want to pause the video and write all this stuff down because you're going to need to know this procedure pretty thoroughly. We're going to do some very intense problems with this in a few minutes. But the basic idea is if we were really doing this in real life, we would take a spectrum and use the Doppler effect to find the speed. We could probably measure the orbital period by just watching the companion star and seeing how long it takes to do an orbit. We can calculate A, and then we can find the mass using Kepler's third law. A big step here that's pretty important is to convert to solar masses. You want to convert your masses to solar masses. You'll be given the mass of the companion star, like the main sequence star, which you can then subtract because we're going to be finding the total mass here. This is our situation where we can't ignore one of the masses. And then it turns out that if the mass of the unseen one is either greater than or equal to 3 solar masses, it's a black hole. We remember that for neutron stars, there's a limit of 3 solar masses that is related to the amount of gravity that neutron degeneracy pressure can support. So we're going to do a couple of examples of this. I'm not going to show quite all of my work, just in the interest of space and time. Try to save myself a little bit of space when I'm doing this. We're going to start with this one that's problem 1845 in your book. You have an exactly similar one on your homework. What we've got is an X-ray binary star. And there's 2 stars, one's a main sequence star, and the other one's unseen. And we've got a separation of 20 million kilometers, which you would, of course, convert to meters, which would be 20 times 10 to the 9 meters. And we've got an orbital period of 4 days. I'm not going to show my conversion right now, but if we do it, we get about 301,000 seconds. And we're going to try to find the total mass. So that's going to be Kepler's third law. We're going to keep both masses in because the masses are going to be similar enough in this case that we can't just ignore one. So plugging things in. And again, I'm not going to show all of my algebra right now because I'm trying to save some space on the slide and save some time. But I really, really, really want you to just sort of pause the video and plug this in yourself so that you can make sure that you're plugging things in correctly. One of the most important things that people mess up when they do this is they don't plug things in right, and so they mess it up. So if you plug things in and you don't get an answer that's pretty darn close to this, then you are doing something wrong with your calculator. We need to check that. You need to talk to me about it. Okay, the next thing we want to do is convert that to solar masses. How many times the mass of the sun is that? And it turns out that 1 mass of the sun, this was kilograms, is equal to 2 times 10 to the 30th kilograms. So I got about 26 times the mass of the sun. Now that's M1 plus M2. This is our answer to part A. But part B, where we're going to do, is we're going to find the mass of the unseen companion and decide if it is a neutron star or a black hole. And it tells us that the main sequence star has a mass of 10 times the mass of the sun. So let's just call that M2. And we know that M1 plus M2 equals 26. So that means that M1 is 16 times the mass of the sun. If that's its mass, that is definitely big enough to be a black hole. So that's a lot of the procedure, but that does sort of ignore the first two steps that were in my little procedure that I wrote down. So I want to do another one with you where we're going to do even more steps. We're really going to separate this out. So again, here's a binary star, and we're told this time that the mass of one is 4 times the mass of the other one. So we could probably say that M2 is 4 times M1 or something like that. We have a separation distance of 10 AU, which if you convert that, that's 1.5 times 10 to the 12 meters. But I'm not given a period. All I know is that an absorption line that normally occurs at 620 nanometers, that's lambda naught, appears at 618, so that's lambda. And we're going to first find the speed. Remember that V over C, Doppler effect formula, is lambda minus lambda naught over lambda naught. Okay, so I can do 618 minus 620 over 620. And I get a speed of about 968,000. Now this comes out negative because it is coming towards us and it's a blue shift. We don't really need that negative, though, to do the rest of the problem, so I'm going to ignore it from here on out. That just tells me that the star is moving towards us, which is not really relevant to us. If I want to find the period, I can do V equals 2 pi A over P. So I can do 968,000 is 2 pi times 1.5 times 10 to the 12 divided by P. And I get that P is equal to about 9.7 times 10 to the 6th seconds. So now I'm in a position to use Kepler's third law. So I'm going to go to here. Plug stuff in. We're keeping both masses. And I'm just going to leave it as M1 plus M2 for right now. I can come back to that later. So frantically plugging things in. That's big. Really not a very good problem, but okay. Get a very large number here. This is a little bit unrealistic, but we'll go with it. Just solve the problem anyway. That's kilograms. I can convert that to solar masses by dividing by 2 times 10 to the 30th. 10,500 solar masses. Again, this is a little bit unrealistic. And then I know that M2 is equal to 4M1. So I can say that M1 plus 4M1 is 10,500. So M1 is about 2,100, and M2 would be 8,400. This is very unrealistic. Stars don't have that mass. But if these were the actual masses, we would definitely say that this is a black hole, not a neutron star, because that's much, much, much bigger than 3. Again, unrealistic numbers, but that's the procedure that you would go through. And that's about as hard as this gets. If you can handle that and just memorize that procedure, you'll be in shape for the hardest possible problems that I would give you on the test on this unit. This is definitely as hard as it gets. Try these on your own, plug in the numbers for yourself and make sure you're getting them right. And definitely ask me questions if there's anything you don't understand in this procedure, because I will ask you this on the test and I will ask you this on the final.